Beyond. Okay, thank you very much. So thank you, the organizers, for the invitation. So my first time in this beautiful town. So today I'm going to talk about, well, mainly my work with Grégoire, which is sitting right over here, which is part of is also part of his PhD studies, and some recent developments with Ruslan Maximov from Montpellier. So I'm going to talk about, well, Verma modules, and just without trying to offend anybody. So Verma module, what is this? So you take your Lie algebra, G, which you can see it as a quantum enveloping algebra or just a Lie algebra. Take a one-dimensional representation of its Cartan subalgebra, which is contained in the Borel, extend it trivially to the Borel. That means ease from your Lie algebra act as 0 on this one-dimensional representation and induce to the algebra. So it's an induced module from a one-dimensional representation. It's infinite dimensional. Okay, so but what I want to talk is about categorification, so higher representation theory. So yesterday you already had lots of reasons to believe higher representation theory is interesting, and it has very nice outcomes. So one of the main reasons is that when you lift representation theory to higher representation theory, you start acting on categories, you have a lot of extra structure that gives you more space to prove other things and to connect, more possibilities to connect with other fields. So it's, known now, evidence shows that higher representation theory has interesting connections with topology, representation theory, physics, geometry, and combinatorics. One of the most popular examples, for example, is the proof by Raphael of the Brouet conjecture that give rise to higher representation theory. And, for example, obtaining Kovanov homology purely in terms of higher representation theory as the Heshetikin-Turaev philosophy. Okay, so let's start doing some math. So pick your favorite quantum Kac-Moody algebra that I always call G and a dominant integral weight. Then there are integrable modules induced, so modules for this dominant integral weight, which we call L of lambda. These guys are irreducible, and if G is a finite type, these are the finite dimension irreducible representations. So everything I will say today is about, it's for G symmetrizable. But if you don't like this generality, which is, well, a class of algebras is huge, you just stick to SL2 or SLN, it's enough to see what's going on. So you can think of G as SL2, for example. So these L lambdas will be the finite dimensional representations. Okay, so here it is. So it's known that all integrable irreducible representations can occur as quotients of Verma modules. So this is a very old fact. So we have integrable irreducible. We have your Verma with the same highest weight, and you have some kernel, which usually can be built out of other Vermas with other weights. Okay, this is interesting, but for each integrable irreducible, we have to pick one Verma that projects onto it, which is, well, good, but we can do something else. We can define what is called a universal Verma module. So this universal Verma module, it's one Verma module that projects to all Verma modules by specialization of the weight. So here, your weight is, well, integral, like here for your Verma module, and here it's a complex. So Q to some complex, to some numbers. Okay, so you can see if lambda is complex, you can see this has a different parameter, so beta, you specialize, and you get your Verma and your integrable irreducibles. Okay, so there's a parameter Q, there are parameters beta coming from the structure of your Kac-Moody algebra. So we think of these always as modules over a field. So these are the field of rational functions to avoid some technicalities of irreducibility and things like that. So the Verma, the universal Verma, will be irreducible. Okay, now it's known that apart from the action, half quantum groups, so the positive or the negative part, I use the negative part, can be seen like almost universal Verma modules, in a sense that Verma modules can be written as quotients of half quantum groups. So there's a quotient map. Now, if you want to write the universal Verma module in terms of half quantum group, you have to add a bit more structure to the half quantum group. So this I haven't defined. It will be clear from what I'm going to say next. So it's something slightly, well, a bit bigger than the half quantum group. Okay, so Kovanov, Lauda, and Raphael have categorified part of this picture. So they have constructed the now celebrated KLR algebras, the quiver-egg algebras, and use them to categorify this picture. So you take modules as explained yesterday and the day before, modules over this algebra will decategorify to the half quantum group, and you can take a quotient, a cyclotomic quotient, with respect to this dominant integral highest weight, and consider modules over the cyclotomic KLR algebra, and they categorify integrable representations, irreducible integrable representations. And we have a quotient map, right? You have half quantum group, you have the simple categorified. Okay, so the plan, what I will try to explain today is how to complete the diagram. So we have to bring the Verma module into the picture. So one part you already know, and the question is what to put here. Okay, now, as I said, and it's well known that categorifications of half quantum group and of the simple integral representations are given through KLR algebras. What are they? So just very quickly a reminder. So we fix a Lie type, Kac-Moody algebra, Dynkin diagram, and integral dominant weight. So KLR algebras can be defined by diagrams, module subrelations. So the generators are just dots, as we already saw them here several times, and crossings. And to the collections of these diagrams, we impose some relations. For example, you have this Reidemeister 2 type move, when you have strands that intersect twice, and in the Dynkin diagram they are connected by a single edge, then you replace this diagram by a linear combination of these two diagrams. So now, if you call nu the sum of the colors, so these labels of the strands correspond to simple roots or nodes in your Dynkin diagram. So the combinatorics of the algebra is encoded by the Dynkin diagram. And so this nu is just a weight, a sum of simple roots. That is the sum of the colors, a formal sum of the colors of the strands. So the algebra decomposes like this, and Kovanov, Lauda, and Raphael proved that the Grothendieck group of the category of modules, some categories of modules over these algebras is isomorphic to the half quantum group, not only as an abelian group, a vector space, but also as a bialgebra. So there's a structure of multiplication and co-multiplication there, and they are also categorified using the Cale algebras. Okay, now what is the cyclotomic quotient? So yesterday you had, it was in someone's talk, you have y1 to some power. So in terms of pictures, that means that you just consider an ideal generated by pictures that contain lambda I dots on the first strand at the left if it's labeled by I. So take a collection of all these pictures, generate a two-sided ideal, and take the quotient algebra. So this is the cyclotomic Kovanov-Lauda-Houquet algebra. Now, action. So there's a natural map of algebras that considers a diagram in R nu and adds a strand labeled I at the right of the diagram. So this is a map of algebras. And this gives rise to two functions of induction and restriction between the corresponding categories of modules. So this is how we define E and F. So we call F the functor of induction, and E is its right adjoint, so it's the restriction functor. So up, we have to add some shifts that I will always forget, but there are shifts involved. And so now we have two nice functors with very suggesting names, E and F, and they have several very nice properties. For example, they are biadjoint. That means the right and left adjoint coincide of one of these functors, and the composites EF and FE satisfy a direct sum decomposition lifting the commutator relation. So this is the SL2 relation, the commutator. So you have these two things together. Biadjointness, which imply they are exact, they automatically induce maps on the Grothendieck groups, and they satisfy, well, an SL2 action, an SL2 relation. So we write this like this. So we have EF, FE, FE, EF, depending on some signs. So we always have to consider two parts of the commutator, because you don't want to have problems with signs. Remember that is EF minus FE. It depends on what term you pass to the right-hand side. And this is just the identity functor a couple of times. We shifted with some shifts such that in the Grothendieck group will correspond exactly to the SL2 commutator with the right coefficients. Okay. Then people ask, what is the decategorification of this algebra with this action? And built on the work of lots of people, like Brandon Stroppel in the beginning for SL2 of level, some fixed level, Brandon and Kleshchev in type A, Lauda and Vazirani in type A, and Kan, Kashiwara, and Webster proved for all symmetrizable type that the Grothendieck group of this category with the action just defined is isomorphic to the integrable irreducible representation. So this was a long way from the half quantum group to this theorem. It's not automatic, it's hard, and it goes through the work of lots of people. I forgot to mention Ariki also, in a non-quantum case. Okay, now from the results of Raphael, you know that we cannot categorify a Verma module from this picture. And the reason is here. Biadjointness and direct sum decomposition. So whenever you have two functors that are biadjoint and satisfy an SL2 relation, whenever you have a highest weight, you will have a lowest weight. So if E kills something on one side, F, a power of F will kill something on the other side. So we'll never get Verma modules. So that people were tended to believe that categorification of Verma modules couldn't be done within this framework. So this was a question from, well, since the time of Kovanov-Laudin-Rookie algebras. Okay, so we need something different. We need to change something. So usually, when you have a set of axioms that restrain your object of study, sometimes if you drop one or two conditions, your world changes. This is true whenever Whenever we have too many rules, if you drop one rule, reality changes. So this is true also here. So let's see how it goes. So the idea is to look at cyclotomic quotients and try to see them as homology of some bigger DG algebra. So we call this enhanced cyclotomic Cale algebra to the DG world. So what you had, we have Calar algebra that projects to a cyclotomic Calar algebra. Now, we say that the cyclotomic Calar algebra is a DG algebra with zero differential. Although this is basically the same, conceptually, these two objects are not the same. So this is an algebra, this is a DG algebra. And now what you can do? Well, do the same to the Calar algebra. Algebra, DG algebra with a zero differential. So in practice, we didn't do anything, but we changed the framework. We're not working in the same framework anymore. Now, the question is to find a bigger algebra with a non-trivial differential, I call it R beta, such that it is quasi-isomorphic to the cyclotomic Calar algebra with zero differential. And it has to contain the Calar algebra as a subalgebra, a sub-DG algebra. So you have an inclusion of DG algebras and a quasi-isomorphism. So the goal of my work with Grégoire was to construct these algebras. So although in practice we didn't do anything, we have a lot more structure now. We have no space to move. Okay, so let me explain what are the extended Calar algebras. So as we start with Calar algebras, and you add structure. Why? This is reasonable because we look for an inclusion of algebras. So we want to see the Calar algebra inside. So let's keep it as it is. It adds things. So we add one generator for each node of your linking diagram. We called it a floating dot. And we're going to place it in the first region from the left, immediately at the right of the first strand. Okay? They can only exist in this space between the first and the second strand. And the label has to match the strand on the left. Notice that since we define functors by adding strands to the right, we see this, our highest weight is at the left, and we act by adding stuff from the right. Okay, so this is close to the highest weight. Right here.
So what do you mean? Because you said you have to place it somewhere special.
Yeah.
You say it floats, so it's a bit...
Because they are in a region, so they can pull it up and down.
Yeah. Just
There are relations. So at the moment you don't know anything, just know that you're going to place these guys in the first space, right?
Okay, so float only in the vertical direction.
Yeah, I will explain, you'll see in the next slide what happens next. So where does these floating dots come from? In SL2, yesterday we saw that to categorify the finite dimensional irreducibles, we look at homology of Grassmannians. So it looks natural in sim Cn, sim C to the n. It seems not natural to look at infinite Grassmannians. The problem is that we don't have an SL2 action in these homologies. If you try to compute a commutator, you only get half of the commutator, half of the right-hand side. So you need to add something to double this value. So we add a new generator, which is Guy, and in terms of homology of Grassmannians, it means that you take the homology of the infinite Grassmannian, just a polynomial ring generated by Chern classes, compute its Cojul dual, and tensor the two together. So these floating dots are the images in the Cojul dual of Chern classes, of the infinite Grassmannian. So this is the only geometric intuition we have for this, for SL2. Even as in the non-Verma case, going out of type A, the geometry gets very complicated. Okay, so this guy floats, and generators and relations. We have to say which relations this guy satisfies, and he only satisfies two relations. It's important. You have two floating dots in the same region, you get 0. So it's an exterior algebra. It's odd. And it satisfies this relation. Whenever you have a Reidemeister 2 with mixed or non-mixed strands and two floating dots, you can move one of the floating dot to the other side with a sign. So this is enough. So in our paper we have a more complicated, very long definition with floating dots everywhere. So this is a minimal representation, a minimal presentation of our algebra. So this is a super algebra. Floating dots are odd, so they generate an exterior algebra. It's multigraded because, well, KLR algebra is graded, and floating dots add each type of floating dot adds a different grading. We call this algebra RB. So this is a super algebra. So everything from now on is super algebra, super modules, super bimodules, super functors, super categories. I will forget the super all the time. Okay, well, I will say just modules, which is easier, but in truth there are super modules. Okay, so we have this algebra. Can do a block decomposition as before in terms of weights. And as I said before, you can add some more general generators, like we can place a floating dot here, and they will satisfy a bunch of relations, okay, which are redundant. The only thing you need is this guy in these two relations. That's enough to define the algebra and the categorical action and compute the Grothendieck group. Okay. Now, oops. Okay. I've been talking about DG enhancement. So here we have an algebra, R beta. But there was a differential. So let me introduce immediately the differential before seeing what this algebra gives us. And for each integral dominant weight, you define a map on this algebra that sends the floating dot to lambda I dots on the strand immediately at its left. So see why the colors have to match. It seems natural from this point of view. And this defines a differential. So we act as 0 everywhere else except on floating dots. Plus Leibniz rule. So this defines a differential, and we prove that the DG algebras R beta d lambda and the cyclotomic KLR algebra, well, in cyclotomic KLR algebra, DG algebra are quasi-isomorphic. So it means that the DG algebra R beta d lambda has homology concentrated in degrees 0. So no superalgebra anymore. And we say that R beta d lambda is a DG enhancement of the cyclotomic KLR algebras. So we have part of our diagram is complete. We know the algebras. And it's clear from the construction that the KLR with 0 differential embeds there. In type A, it's easier, but a lot out of type A, you have to go around. You have need bases and check carefully that it's. Yeah. No, it's not easy. Yeah, outside of SL2, it's hard. Okay, so now define category of modules. Notice that I didn't say, but scalar algebras are infinite dimensional as K modules. K is the field we already defined, and cyclotomic scalar algebras are finite dimensional. The algebras we're dealing here are infinite dimensional. And you want to categorify a Verma module. So if you know the right-hand side of the commutator contains a fraction, which we see as a power series. So this says that we need infinite objects with infinite dimension. So let's define this category of modules. So left bounded, so gradings bounded from below, locally finite dimensional. So in each grading, multi-grading, they are finite dimension. Left modules with degree zero morphisms. And we also ask the grading to fit inside a cone, because we're dealing with objects with infinite resolutions. And the Grothendieck group you want to define has to be, well, topological. In order to have convergence, you need to restrain this grading. It's some technical thing to make things well defined. And if you put a P there, we just look at the full subcategory of projectives. Now, another ingredient to the picture, we can place diagrams side by side to produce a new diagram. The problem, not a problem, but one can ask, this guy has a floating dot that is to the left, right? But you know how to turn general floating dots in terms of floating dots to the left. So you put these two together, we define a bigger diagram, which is in the other presentation I didn't give, push all floating dots to the left, and you get another diagram. So you have some horizontal composition of diagrams. You have to be careful because floating dots have gradings, and you have to be careful on what version of this enhanced scalar you put to the right to make things match. But we have this map, and we have an isomorphism of algebras between the Grothendieck group of this algebra and a bigger, so the Grothendieck group of this algebra, where you sum everything, you sum over all possibilities of shifting your highest weight, gives you some version of u dot minus, which is somehow, so you take the whole algebra, you can take the idempotent version, and then only take half of it. This is what you get. So it's just half quantum group shifted, with the weight lattice included. And with this, we know how to project two universal Verma modules, because the extra parameter is already here in the idempotence. Okay, so you define m beta as the sum of all this collection of modules, and define a functor exactly as before. No, it's just another parameter. It's q to some complex.
Right there, it's just a notation. Because when you define R beta, there's no beta.
It's the grading of the floating dot. The grading you create.
Is there no differential there when you say R beta, or is there a differential?
Yeah.
Everything is when you talk of modules, the next page, when you talk of the category of modules, when you talk of modules, you mean DG modules, or you mean next page? I think it's the next page. Can you go to the next?
Yeah.
So R beta of nu.
Yeah, this is over RB without differential. With no differential.
When there's no differential, it does not depend on beta. Is that correct?
Beta is the grading of the floating dots.
I think I understand what your question is. So you have this super algebra of beta, where you can add a grading for all the floating dots, which corresponds basically generating highest weights. And then you can specialize them. So you say, okay, beta 1 is high and 1, and you introduce the differential. Just d lambda difference. it out and get a DG algebra and it can get more fit inside the conclusion.
Yeah, but this part is not that.
This part
It's not. There's no differential here.
But then it's, I'm just asking whether the category there depends on beta or not.
No.
It depends on beta.
Well, beta is a grading.
it's like
Doesn't depend on beta, it's just a different grade. Okay.
Okay, okay. So we want to define an action on the algebra. There's no differential here, so the enhanced algebra. So we do the same thing. We add a strand to the right and call it f, the functor that it gives rise, f, and the adjoint, we call it e. Now, these functors are also nice, but not as nice as in the previous case. So they satisfy a short exact sequence. So we have fe inside ef, and then you have a quotient that contains two terms. What is this? So q of nu is just, it's an infinite coproduct. You can see it as infinite direct sum, which you can do in our category, because everything is filled, it fits inside a cone. Direct sum of the identity functor with shifts, such that in the Grothendieck group, so we have q of nu applied to something would correspond to multiplication by 1 over q minus q inverse of this, roughly. There's some nu there that I want to just, means that on which weight space you're acting. So this is half of the commutator. Now you add a shift in q, which we don't care the explicit form, and a shift with in the second degree, in the second grading. So this gives you a lambda. And you have this twice, but now you have a shift of -1. So it gives you lambda -1 over this, which is the SL2 commutator. This is for all I, and you have the usual stuff if they're not connected in the Dinkin diagram. And this exact sequence does not split. We don't have a map from here to there in our category. It doesn't exist. And also from the right-hand side to the middle part. You only have a map from one of these components here. So we don't have direct sum decomposition of EF plus FE with the quotient, with this tail. It doesn't exist. And this is different from what we had before. And the difference comes out here. No biadjointness. We don't have biadjointness as well. So we did only a junction from one side and no direct sum decomposition. So whenever you have a highest weight, you will not kill a lowest weight. Because Raphael's arguments don't apply here because you don't have biadjointness. They are exact, yes. Yeah, and they form an adjoint pair. So they are exact. They induce an action on the Grothendieck group, the topological Grothendieck group. And with this action, we have an isomorphism of representation. So I forgot to erase this guy. For me, G is already the quantum. So this gives you categorification of Verma modules for all symmetrizable types. Now, let's have a look at this exact sequence with the differential. So now we bring in the differential into the picture, and you still have a short exact sequence of DG functors. There's a differential here acting on the sum that makes this sequence a sequence of DG functors. Now you know the homology of these terms. We can compute them. These are DG bimodules. The differential is very explicit. You can compute the homology. And we know that in homology, we'll end up in the cyclotomic KLR world. Okay? And next, we have to look at the right-hand side. But we have a short exact sequence of complexes, DG. So you'll have a long exact sequence in homology. So the long exact sequence splits depending on the sign of this parameter that occurs in the construction. Even in the Kashiwara construction, this guy is there. Depending on the sign. And in Kashiwara and in Raphael's talk today, the sign of this will say which direct sum decomposition you take. So if you take a paper on higher representation theory of Katsumudi algebras, you only have the commutator in two formulas, not one. I only gave one. And where does it come from? Why do we have two? The sequence splits, and depending on the sign of this guy, the homology of the last term is concentrated either in degree 0 or 1. So if you have one sign, we have one type of sign plus, for example, this guy is concentrated in degree 0, and you have this formula coming out of long exact sequence. If you have the minus sign, you'll get a different formula because the guy on the right is concentrated in a different degree. And this is Kashiwara and Webster's two commutators. So it comes out naturally from this. In our point of view, it's easier to do this than to do Kashiwara, what Kashiwara and Kang did. Once you have the long exact sequence and well, but now they come from the same place, as it should. If you have a Verma module, you know it projects to you only have one formula for the commutator. It projects to the finite dimensional representation, and then suddenly there are two formulas.
The induction thing, in some sense, is not compatible with the differential, because you don't have a multiplication or a constant structure on the Verma module. Is that correct? I mean, not, yeah. Once you put the differential,
you can do it. Yeah, yeah.
Yeah, I understand why. But is there so it's the normal numerical algebra depends inside, but is there a choice of differential for which you get back the numerical algebra or not? No, never.
No. It's just one direction. Okay. So we have these relations between our functors. So it's the action on irreducibles. Now we go to the appropriate derived category of compact objects, and then you have an isomorphism of representations. Okay. So now we finished what I was promising. We have a diagram, we have a categorification of the universal Verma module, and you know all maps. All things are connected. But it happens that there are more types of Verma modules. So instead of inducing from so our Katsumudi algebra consists of several Ks. Several Fs, and I wrote it like this, several E's. So the part generated by the Ks, this is Cartan. Ks and E's, it's Borel. And then we have the whole algebra, which is not true. We have intermediate steps. So we can consider a bigger algebra that contains the Borel. So let's say here. And you call this parabolic. So a parabolic subalgebra is an algebra that contains a Borel. Now, to define Verma modules, you stick with one-dimensional representation of the Cartan, and you reduce trivially to the Borel, okay? But now, since you add some f's, you have something here, which is a Lie algebra. The case, all the f's that correspond to the parabolic and the corresponding e's. So this is Levy. So now instead of looking at representations of the Cartan and induce, you look at reducible representations of the Levy, which is Lie algebra. And then induce trivially to the parabolic, and then to the whole algebra. So this is a parabolic Verma module. So it's something more general. This is roughly the picture. But you're not forced to start with a one-dimensional. So this is commutative. You don't have to start with a one-dimensional representation. You can start with, let's say, finite-dimensional representation. And then induce. We can use infinite-dimensional representations. It will also give you another type of Verma module, which is even more general than parabolic Verma modules. So generalized Verma modules. So these are highest weight modules. All Verma modules are, are there. And one might ask that can we categorify them? And from our picture, it's somehow straightforward. Instead of adding a differential that sends all floating dots to polynomials, we only send some floating dots to polynomials. Notice that you have, when you induce, you have f's, directions, that give you something finite dimensional, and then you have the other guys that will connect forever and gives infinite dimensional tails. So these are the guys you want to make disappear with a differential. So this is this formula. Let's say that IFN labels the roots that belong, that correspond to your parabolic subalgebra, and then you only act with the differential non-zero in some of them. So these give you a mix between the Verma categorification and the cyclotomic KLR. Because for these roots, you have a cyclotomic KLR inside, which makes sense because a parabolic Verma module is somehow a mixed between a Verma and a finite dimensional representation, or integrable representation if you're not in finite type. So this construction works and results in the categorification of the parabolic Verma module. So here Vn is just the module we used in the beginning. Okay. So parabolic Verma modules can be used to construct linked invariants. In particular, we obtained, this was not the purpose of the talk today, you can construct Ohmfli homology, Kovanov-Rozansky-Ohmfli homology, using parabolic Verma modules. So using representation theory, you can use them to prove some theorems there, some conjectures. So another reason for studying higher representation theory. Okay, now this is what is known, it's outside, it's on the web. In type A, one of the major breakthroughs of Kovanov-Lauder-Rouquier algebra was the proof by Brandon and Kleshchev that there is a grading in the representation theory of the symmetric group. So they used KLR algebras to prove this, which people suspected from a long time ago, but there was no explicit construction. And the proof, this construction, goes through an isomorphism between scalar algebras of type A and Heck algebras. So in particular, we call these quotients cyclotomic quotients because the cyclotomic scalar algebra in type A is isomorphic to cyclotomic Heck algebras. That's where the name comes from. And this was the work of Brandon and Kleshchev and Raphael. It's already in Raphael's paper, this isomorphism. So we call it. So take KLR world, KLR algebras that come from something different. Okay. And then in type A, suddenly these scalar algebras are Heck algebras after completion or localization. So whenever you have something scalar type, one can ask what's on the Heck algebra side. So what I'm going to explain, well, the next minutes is what is the Heck algebras that correspond to these new scalar algebras that I explained. Okay, just let me recall you what are affine Heck algebras. So take a field, algebraic closed field, fix an element Q in the field, and a natural number D, and now define an algebra HD, which depends on this Q as follow. Is Q equals 1? We don't start with the algebra and then look at the parameter. We use the parameter to say which algebra is there. If Q equals 1, HD is the degenerate affine Heck algebra over K, which is generated by S1, SD minus 1, and x1 to xd. So, module sum relations. Relation says that the S generators generate the group algebra of the symmetric group. They satisfy the symmetric group relations. The X's, well, it's affine, so there's a polynomial ring inside. The X's generate a polynomial ring, and there are some terms mixing them. So we already saw relations yesterday in Raphael's talk. Where's the... One of the relations is that you have xi, si minus si x1 plus 1 is the identity. So it's a lot like scalar algebras. But notice that there's no apparent grading here. The algebra is not graded, okay? If Q is not 1, then we say that HD is the non-degenerate affine Heck algebra. So this is what Katerina called extended affine Heck algebra in her talk. So generators T1, TD minus 1, and X's plus minus 1, module relations. So the relation says that the T's generate a finite dimensional Heck algebra. So they satisfy the Heck algebra relations. The X's form a Laurent polynomial ring, and there are some relations like this, a bit more complicated with Q involving Q's. Just let me stress that degenerate affine Heck algebra is not a affine Heck algebra with Q equals 1. These are two different algebras. They have nothing to do with one with the other one, except if you do some appropriate quotients. Okay? So the size is obviously different. Okay? So I use Q equals 1 and Q equals minus 1 in order to use the same notation. So at the end, we're going to have only one statement. Okay, so this is this algebra that show up almost everywhere. And now we want to do what we did with the Calar algebras. So we look at cyclotomic versions of these algebras and try to DG enhance them. So before the differential and the cyclotomic, let me say what we do, what is the corresponding, what corresponds to floating dots here. So we had a new variable, which is odd. So we want a superalgebra. This is odd. And impose some relations. So it squares to 0, it's odd. So it commutes with all the polynomial variables. it commutes with all the SIs except for the first one, and then there it satisfies this relation. This is for the degenerate affine Eck. So this is almost the same sort of relations we had in the KLR. So if you draw string diagrams for permutations, this relation gives you exactly the same picture, not the same meaning, but the same picture as in the extended KLR case. So this is Q equals 1. For the affine Eck, one of the relations is different. We had an extra term. Okay? Although for Q equals 1 we have the same relations, these are distinct algebras. Okay? This algebra exists for all Q, but has nothing to do with KLRs. Okay, now introduce a differential. And we have two formulas, one for degenerate affine Eck, another one for affine Eck. So send everything to 0 as before, and this new generator is sent either to this polynomial, where lambda I is an integral dominant weight of Lie type A infinity, or to this guy, where here lambda is of type of affine type, so cyclic. So degenerate affine Eck algebras correspond to the infinite linear quiver, and affine Eck algebras, closed quiver, just a cyclic quiver. So the DG algebras, well, HD and HD with this differential they are isomorphic to cyclotomic Eck algebras. The same thing that we did in the KLR case, the same sort of proof. We have basis for these algebras, so you can do the computation exactly as we did in the KLR case. So these guys are DG enhancements of cyclotomic affine and degenerate affine Eck algebras. Actually, we can replace this by more general eigenvalues for the polynomial action, and it works as well. So this is what is exactly used in Brendan and Kleshchev's paper, but there are more general versions with more general eigenvalues. But this makes clear the connection between Eck and KLR. Okay, now either you can localize both algebras with respect to something, or complete, take a completion, as is done in Brendan and Kleshchev's paper and some papers that from other people that came out later. Then the Eck algebras get a block decomposition. You get idempotents. You can look at blocks. And the blocks are labeled by elements of n of I. I is the quiver, the Dynkin diagram. Differentials, leave two differentials on these completions. So, work in progress, it's not finished yet. We had this idea some time ago, but there was lots of things that put in between, so it's not, so it's work in progress. KLR, completion of KLR are new, and completion of this Eck algebra with this block corresponding to the same weight are isomorphic, as Brendan Kleshchev-Hooke's isomorphism. This is mimics other constructions, so you have to keep track of what you do to the theta in the isomorphism and check that we have isomorphic algebras. And moreover, the next plan is to prove that, this is our conjecture, they are not isomorphic only as algebras, but as DG algebras. This is harder. This is harder. We're still working on this, so this is conjecture. Because Brendan Kleshchev-Hooke isomorphism, so it's not straightforward. And algebras are complicated. So we need to keep track of the differentials everywhere, and it's not obvious. Of course, if you have this isomorphism, we can use the isomorphism to cook up a differential. If you have a differential on one side, you can bring it to the other side. But you want to check it corresponds to the one I have induced, which seems more natural from the egg point of view. And that's it. Thank you. We already proved. So there's a spectral sequence from G Humphrey homology to SLN homology that collapses.
This is already proved with this construction.
Yeah, with the previous paper by Grégoire.
I lost my thought on this point.
Yeah?
So can you use the new algebra, the affine algebra, the extra data, and the differential? Do you think it could help to understand the center? You know, there's this conjecture that's still not proven about the center of the centers of cyclotonic regular algebra.
It might.
I mean, you have to be overseas, so you don't want to go to, you don't want to use categorical algebras, whatever. I mean, you want to use just this new algebra. You use the cyclotonic regular algebra rather as a homology of the big algebra.
It might be. It might help. Yes. Okay, it might help. Thanks. It might help because now you have more space to move before projecting, and then yes, thanks.